This is the Composite Figures and the Coordinate Plane tutorial. In this tutorial, I'm going to teach you how to work through several problems dealing with composite figures and the coordinate plane. In our first problem, we're asked to determine the area and perimeter of only the shaded region of the figure below. Well, you can tell that we're dealing with a regular pentagon, and the distance from the center of the pentagon to one of the vertices of the pentagon has a length of 3 centimeters. And the length of one of the sides of the pentagon has a length of 4 centimeters. So there are two ways that we could go about solving this problem. We could determine the apothem and the perimeter of this pentagon, solve for the area, and then take 1/5 of that area, since this shaded region right here is 1/5 of the total pentagon. Or we could create a series of two triangles here by finding the apothem in the shaded region and finding the area of both these two triangles and adding them together to solve for the area of the shaded region. Let's go ahead and use the latter method. So, in order to determine the area of these two triangles, what I first need to do is solve for what this angle is right here. In order to do that, I'm going to use the formula that the interior angle of any regular polygon is equal to 180 times the number of sides minus 2 divided by the number of sides. So in this case, we have 180 times 5 sides minus 2 divided by 5. So we have 180 times 3 over 5. So 180 times 3 is 540 over 5 is equal to 108. So each of the interior angles has a measure of 108 degrees. So each one of these guys is going to have a measure of 108 degrees. Which means, since these angles are bisected, that this angle and this angle each have a measure of 54 degrees. Now we'll use that and what we know of right triangle trigonometry to solve for the apothem here, the height of this triangle. What I'm going to do is just redraw one of these triangles right over here. So here's one of those two identical green triangles drawn off to the right. You can see that we have our 54-degree angle here and our 90, and we know that the hypotenuse of this triangle has a length of 3 centimeters. We want to solve for this side right here, which was the apothem inside that triangle. So what we can use is the sine trigonometric function. The sine of 54 degrees is equal to the length of the opposite side, which in this case is our apothem, divided by the length of our hypotenuse, which is 3. So what we want to do first is just find the sine of 54 degrees, which has a value of 0.81. And that's still equal to our apothem divided by 3. So we want to solve for our apothem, so I'm going to multiply by 3 on both sides of the equation, and we're going to have 3 times 0.81, which is 2.43. So that's the length in centimeters of our apothem. And we know that our perimeter is just 4 centimeters times the 5 sides of this pentagon. So 4 times 5 is 20, which means that our perimeter has a length of 20 centimeters. So now you could go either way. You could solve for the area of the entire pentagon and divide by 5, and that would be the answer for the green triangle. Or you could just use what you know of the area of a triangle, 1/2 base times height, and solve that way. Let's actually just finish it up by using the formula, the area of a pentagon is equal to 1/2 the apothem times the perimeter. Our apothem is 2.43, and our perimeter is 20. So we could just take 1/2 of 20 to make this easier. Half of 20 is 10, and 10 times 2.43 is 24.3. We just had to move the decimal one place to the right. So the entire area of this perimeter, or of this pentagon here, is 24.3 centimeters squared, but we want 1/5 of that. And 1/5 of that is 4.86. So the area of just the shaded region is 4.86 centimeters squared. Now let's move on to our second problem. In this problem, we're asked to draw and then classify the polygon with the provided vertices. And we've been given these vertices A, B, C, and D down below. So the first thing we want to do is bring in a graph. And then we want to plot each of those points on the graph. So I'll just begin with A. A occurs at 1, 1. So I'll go 1 to the right and then 1 up. And I'll write that as point A. B is at 3, 3. So I'll go 3 to the right and then 3 up. And that's our point B. C is at 5, 3. So we'll go 5 to the right and then 3 up. That's our point C. And D is at 3, 1. So 3 to the right and 1 up. Now that we have the 4 points plotted, we want to connect them to form a polygon and then identify that polygon. So I've connected those 4 points. And what it looks like we have here is a parallelogram. You'll notice that these two sides are congruent. They both have a length of 2. These two sides are congruent if you calculate the distance between them, but I can tell because they both go 2 over and 2 up. And they also have an identical slope because they go 2 over, 1, 2 from point A, and then 2 up to point B. And the same thing from D. You go over 2 and up 2, which means you have a slope of 1. So both have a slope of positive 1 in this case. So what we're dealing with here is a parallelogram. Now let's move on to the third and final problem of this tutorial. In this problem, we're asked to estimate the area of the provided irregular shape. There are 2 ways to approach this problem. You can either go through and mark off each full box, so 1, 2, 3, 4, 5, 6, 7, that kind of thing, and then count it all up and then add in all the partial boxes when you're done. Or you can box it off in a big box, the ones that are full. So for example, you could go straight down here, because these are all full, and then straight across to about here, and then straight up, and then straight back across again. And you could solve for the area of this box and do that several times, then count up each individual box. Either way is fine. I'm going to use the second method. So I'm just going to go through and put in square boxes here that I know all the boxes inside are filled in with that orange, so that I know that they actually contain the area of this puddle-shaped figure. So let me put in a couple boxes here for you. Now that we've drawn in all these big boxes, we can write in the area of each of these boxes. For example, in this smaller box off to the right, it's 2 units across, 1, 2, and 3 units down. So 2 by 3 on a rectangle would have a total area of 6 square units. So we can do the same for all these boxes. Like this guy, for example, is a 2 by 4, so it has a total area of 8. This is a 1 by 3, which is 3. This is a 1 by 7, which is 7. And this big guy is a 7 by 8, so it has a total area of 56 square units. Now I'm just going to put an X in all the individual single squares out there. So here's one, here's another, and one last one right here. So there's a total of 4 of those. And let's add everything up over here on the left-hand side. We have the big box of 56 square units, then 8 square units, then 7 square units, then 6, then 3, then 4 individuals all by themselves. So the total perfect square units is 84 square units. Now we want to take a look at all the partials, and we want to try to add all those up approximately. So I'm just going to put a couple together. For example, These three here, I'm going to call 1 unit. These two look like they could add up to be 1 unit. This one right here and this guy make 1 unit. Then we've got maybe 3 units right here. Half a unit right here, and half a unit right here makes 1 unit. Looks like this is 1 unit. These two probably make 1 unit. This guy and right here could make 1 unit. Here and here could make another. These three probably add up to 1, and these three probably add up to 1. So let's total all those out. So if you were following along with me, it looks like we have about 13 more square units. So if we add that to the others that we already had, we get a total of 97 square units, and that's an approximate amount. Where something like this could be used is if, let's say there was a giant oil spill in the ocean and you were looking at it from a view overhead. Let's say a satellite takes images of that oil spill, then people can actually lay a grid down like this on it and approximate the area that that oil spill is covering. So if this were maybe square kilometers for each of these units, it could cover 97 square kilometers out in the ocean, something like that. Now these are a challenging problem just because they're time consuming. It's nothing terribly difficult, you just have to kind of put some time into them.